Hello, welcome to Social Educational Project, School of IT Professionals ProfIT, based on National Aerospace University Kharkiv Aviation Institute. Today we are going to talk about machine learning, and we are going to talk with Sergey Bobrovskyi from Airbus from Germany. Hello, Sergey.
Hello.
Thank you for your time for us. I wouldn't spend more time, and the stage is yours.
Okay. Hi, Dmitro, and thank you very much for the invitation. So I will be speaking in English, since it's much easier for me, but I can understand and speak Russian, so the questions can be posed in any language. I will be talking about anomaly detection on industrial time series data. Which is an interesting topic for us in Airbus, but it's also an interesting topic, I think, for many applications in the industry. Let's see. So, why do we care about it? So, anomaly detection is about patterns in data which are not conforming to expected behavior. And usually, these are very valuable patterns to discover because the actions you derive from them create tremendous business value, but also can create value for humans in general. Starting from the left, let's see if you can see my mouse here, like, I don't know. Oops. Starting from the left, you see a picture of retina. So it's of pictures from human eyes. And you see nominal behavior here, and you see here areas shown in red, which are detected by our algorithm to be not nominal, so to be an anomaly. And this anomaly corresponds to retinopathy. So it's a fluid which gathers behind retina. And this is, of course, a medical condition which has to be treated. So by detecting this anomaly, you allow humans to be healed, which is tremendous gain in life quality. So by detecting an anomaly and taking and deriving an action out of it, you create something valuable. The same is the picture in the middle where you see electrocardiogram. So this is what you, if you go to a doctor and the doctor starts to examine your heart, this is what he's usually doing, or she, creating this kind of pictures. And you see in the middle a collective anomaly. So clearly the pattern in the heartbeat is different from the others. And this is a premature atrial contraction, which is also a condition which has to be treated in some sense. So from these examples, we see that if you can find something like this, these patterns in data which are present a non-expected behavior, and if we can make out of it, take a decision and do something about it, we create a lot of value. And on the right-hand side, you see an example from our industry, where here we focus on this red curve here, where you see there is an oscillation and then nothing, and here we see just this oscillation. And compared to the left, actually the right-hand side is an anomaly, while the left-hand side is something expected. I will come later on why the same pattern looking from here to here might be an anomaly and might not. But also here, this is an oscillation in a valve. You should not be there. If we detect it on time, we can perform a maintenance and we can save money. So I think the anomalies are so important because this is something where if you make a right decision after detecting it, you can either save money for your company, you can save lives, or you can at least predict the future evolution and see that something might break. So now I will focus especially on time series aspect. So it might be a boring topic compared to what other companies are doing, for example, Facebook, Amazon, and the others, where you have you have analysis on pictures, you have analysis on speech, on text. Time series are this boring looking data where you have sensors which record data in time. So this is the time axis, and at each time you record one value. It starts to have these patterns, and you analyze all of these patterns. But this is the data which is generated by the industry. So this is the beating heart of the industry, similar to the electrocardiogram by your doctor. All of our assets, the planes, many sensors in the planes, but also all our manufacturing assets, if you equip them with sensors, will produce this data. And if you, as in the case of the doctor, if you are able to detect when something is not healthy, then you can derive from it some kind of action. And if you perform this action, you save money, or you even create new business opportunities. Okay, let's start to be more technical. So we want to detect anomalies. So we want to detect patterns in data which are not expected. How do we do it? First, we have to understand what is actually normal, what it means to be normal. And then, of course, you compare it with, starting from this definition, you can go to what is an anomaly. So usually you define a region representing normal behavior, and any observation which is outside of this normal region is by definition an anomaly. So here is an example from, here are some references for you. So let's do a little bit mathematical. We have two features, which is machine learning, it's called features, but this is essentially a dimension where you can structure your data across it. Assume you have 2 dimensions. And all of your data, you see if you, one data point in this, this is one data point. And so we have these 2 big regions where all the data points fall, and 1 and 2 here, and then 1 here. And clearly this is the majority of points. So by definition, this is normal. And then we have some individual points here, O1, O2. So these are individual anomalies because they're clearly outside of these big gatherings. And then you have a collective anomaly here where there is a smaller cluster of points in this kind of dimension. And already from this picture, if you would be able to draw lines here and divide these points from the others, or the lines are drawn actually here, which are essentially defining the 2 normal regions, and everything which is outside is an anomaly. But already stated here, it's quite hard to define a normal region that encompasses every possible nominal behavior. What about this region here? Maybe you just haven't have enough data, and if you would gather more and more data, this region might become larger. And this is just a condition of your system which happens not as often. And then, of course, you need, at least in order to test it, you need to know beforehand where you had anomalies before. Every algorithm which you develop, you have to test it somehow. And so you need what is called labeled data. So I'm not sure if all of you are within this, you know, this jargon of machine learning, but labeled data means that you have data where you know the true value of it, whether this data point is anomaly or not. So in this plot, if I could color the points by being anomaly or not, and if I clearly see that, for example, green color standing for nominal data, and these points are all green, and these points are truly green, and these are, for example, red, not nominal, then I know the truth. Usually you don't know the truth, and you at least need some small set of samples where the truth is known, that is so-called labeled data. Usually it's extremely hard to get in this context of industry, because the labels can be only done by engineers who really know the system you try to investigate. And if it's not working, then, so usually it takes a lot of working hours for them to provide you these labels. And then there is the next problem, and this is this small context-dependent deviations. And we'll look again at example in the beginning. This is actually here a temperature or something like this. And you see an oscillation here, and then the oscillation dies out. On the right-hand side, you see a same oscillation. It looks very similar. And the left example is normal, and the right is anomalous, and we are interested in this one. And why is it the case? Well, the expert would say to you, here in the upper half, in the upper plot, you see in this orange box, that there is a binary parameter. So this is a variable which takes the value 1 or 0. So this is actually a switch which a pilot can turn off or on. And if there is a switching, like here from 1 to 0, then this behavior is expected. This is the answer of the system to the switching. While here, nothing is happening, and the system but the system starts to oscillate without any input from outside. So this is an anomaly. So the same pattern can be anomalous or regular depending on the context of other variables. This is called context-dependent deviations, and they are very hard to understand. And what this means here, this is actually an oscillation. You can imagine this is a valve somewhere, and this valve is still, it's not breaking the airplane, it's operating. The plane is always safe because we are speaking here about small deviations, nothing which is safety relevant. But still, this means that there is an opening and closing of this valve many times per minute. And of course, the valve is designed for a nominal amount of opening operations. And if you are operating it continuously without need, then the lifetime of this part reduces. So it has, if designed for 1 million opening and closing, and you have reach this million much earlier than expected, then it will probably break earlier than expected. And as you know, right now in the crisis, many airplanes are on ground, and it costs a lot of money for the airlines. So in any time, if you have unscheduled time on ground, where the airplane is on ground, this is a major financial impact. So this is we want to avoid. We want to understand when this happens, and either to prevent this or to schedule maintenance in a way which is which can be planned and not ad hoc. And of course, if you think about this in the context of like data science challenge, we want to speak about data science. We want to speak about how to do it not manually, but by an automatic system. You need the data. And so at Airbus, we are quite lucky that we have a unified data ecosystem, which is also open to customers, to airlines. So they also provide their data inside. And this system is called Skywise. It's a unified data ecosystem. And sorry. We have now a connected aircraft where this is the case for the A320, which is called a single aisle aircraft. And we have 24,000 parameters and 100% of available data points. We also have operational environment data inside. So we know what was the temperature about, what was everything on a lot of information of environment. We know in service data, so the data which is generated by our customers, by the airlines, while the plane is in service. We have industrial data, we have data from production process, a lot of financial, so everything which company is generating in terms of its operation, supply chain data, and so on. So you need the data before you start any advanced machine learning operations on your system. And now let's get a little bit technical, since this is a little bit a lecture. So our goal, so we have defined our problem. We want to find patterns in data which are not expected. In order, first we define what's expected, and then everything else is considered to be anomalous. So we have our time series, which can be looking like this. So we have time dimension on the x-axis, and then we have different data points. First thing we can do is we can just sample it and take one data point and create a very long vector where if it's, for example, if it's 1 million seconds, you have here 1 million readings for one sensor. So this is just 1 million dimensional sensor where you just create a vector. So usually I will denote, these gray boxes will denote vectors, and these are random entries, so like entries, the value of the sensor at each time step. So we lose a little bit the time dimension. We are now in 1 million vector dimension. And of course, this is something you cannot work with. So usually what you do a dimension reduction. So you try to find a basis in the space of this vector. You assume somehow there's something akin to a vector space. It's not really a vector space, but you assume you can do something like this, that you can reduce the dimension of this vector going from millions of dimensions to 3. So maybe you create new features out of it. For example, create summary statistics. So you create a new space where you compute, maybe you have 1 million time readings here, but then you compute mean value, median, you compute quantiles, you compute quadratic statistical features, and so you come up with 10-dimensional vector. Or you do something different. You can create a basis. You use wavelets, for example, or you use Fourier transform. So you go to a different dimension and then you perform dimensional reduction. Or you use functional principal component analysis. The same here. You have a functional basis which is adopted to the data. This is FPCA. And then you go to a subspace here shown going from 3 or maybe dimension to 2 in this plane. So you go to a lower dimensional subspace and you try to analyze your data in the subspace. And if you're lucky, what happens is you get a plot like this. So you see that if you take your data points, so each point here is now in this space is one whole flight or one data, like you have thousands of such samples and each data point is one such sample. If it's easier for you, you can think about it in terms of flight. For you have a reading for one flight, for 2, for 3, and each flight is one data point. So these are actually 3 principal components, functional principal components shown here. And then it turns out that majority of your data is in this ballpark. So you have a majority here, and then you have more points outside. And you will, by definition, say, okay, I will consider everything. The majority defines what is normal, and everything which is far away. So you have a distance here. So you do something like a clustering and separation. And if you separate points, you will say, okay, these are my anomalies. So this is how anomaly detection then works. You try to find a lower dimensional representation, which is quite somehow captures the essence of your data, and then you just see where the majority is, and you then put a plane here or whatever and say all these points are anomalies. And in this case, you see we have a color because this is labeled data. So the color tells us what is true or false. And the green points are really nominal points. We know it because somebody analyzed the data before. And the red ones are anomalies as well as these points are anomalies. And we see that if we were blind, colorblind, and wouldn't see the color, probably we would mislabel these 2 points. We would consider them to be one cluster because they're very close to the green ones. But we would correctly identify this for anomalous things. So this is how regular pattern recognition techniques work in this field. So you try to go to a lower dimension, you try to find the right basis, and then you just see where the majority of points is, and you separate the others away and consider them to be anomalous. Okay, but I want to speak with you about deep learning techniques in this field. What is the technology behind? And I don't know how much you have heard about it or what is your knowledge on deep learning. So I will try to give an introduction to it, which should be hopefully for somebody who understands math and know mathematics and how computers work, a little bit helpful. Usually what you see when people talk to you is this kind of picture of a human brain. So this is a neuron in human brain. And of course, the developers of perceptron's first modules here, and this is how you usually see a neural network depicted. And I will tell you why it's shown like this and what this means. So the initial idea came definitely from the investigations of human brain. So this is a neuron, and the neuron has kind of input, which are dendrites, and an output, which is the axon. Electric signals come to dendrites, and if the sum of the electric signals is higher than a certain threshold predefined, then an electric pulse, a binary pulse, which is called spike usually in neurological literature, is being ejected. This spikes, so this is an on-off signal. Either the sum of the inputs is high enough or not. If it's not high enough, the spike is not generated. If it's the sum of inputs is high enough, then the spike is generated. It's always the same height in this usually, and then it dies off. So this is called action potential or spike. And so these things, registered inputs, if there is enough, the threshold is crossed, it creates an output. It goes through the axon, and the axon are connected to the dendrites of the second neuron. And then it fires again and again. And so you have a very orchestration of these firings. Going back to the left-hand side, this operation can be understood as something called linear map combined with a nonlinear function. So essentially, what you see here are layers, and each bubble with the things attached to it is actually a neuron like this. So you have an input, and these are, for example, 3 numbers, or this is one vector which will, so we have a vector like this, and you just draw it horizontally. So these are maybe 3-dimensional vector going in. And then these lines in between are essentially just a matrix multiplication. So this thing here receives input from here, here, and here. So each of it receives input from all the input layers. If this input is larger than some threshold, this thing produces an output. So usually the activation function here is very similar. And then you stack it on top of each other, and on top of each other, and on top of each other. And these are called hidden layers. And then you compute your output, which is just one number maybe, and you train on data examples. Let's see it in more detail. I think it was maybe a little bit not clear right now, but we look at now in detail what happens. Okay, so now we look from right to left, because this is how multiplication in mathematics usually work. Our input is a vector. So in this 4-dimensional things, it's usually a vector. What is happening in the first layer is that you have a matrix here. This is a matrix, and the color indicates just whether the numbers inside are positive or negatives. And this is something very close to 0. So you take this vector and you multiply it by the matrix, which is the usual matrix multiplication. So this one is multiplied by this one by this one, you sum them up and you get the first result, and so on. So matrix multiplication, and you get the result of matrix multiplication, which is a linear map. Then usually we have a constant term which is subtracted from it, and then you apply a nonlinear operation on top. And usually this nonlinear operation is a so-called rectangular linear unit. So if the result, and this nonlinear operation is applied to each element of the resulting vector separately. So if something is below 0, it's being mapped to 0. And if it's above 0, it's just mapped to itself. So this is a diagonal, and this is our horizontal line. So if we go back, now you can see, okay, this is positive, it stays the same. Zeros are mapped close to zeros, and all the negative numbers are mapped to zeros. Then you have a hidden layer. So this is what you usually call hidden layer, which is giant matrix here. The layer width is quite large. So this is, of course, this is the input width, and this is the width of the output layer. And again, you perform matrix multiplication, you get a nonlinear function, you get an output, and then you can stack it on top of each other. And this is how this picture is being generated. So matrix multiplication, nonlinear functions, matrix multiplication, nonlinear function, and so on and so on. So you stack them on top of each other. And this is also thought from how the visual cortex in human beings is structured, more or less. And the big trick about it, the magic, is that we do not specify the values in these matrices. They are random in the beginning. What we have, if we're training a model with labeled data, we have the input and we have the desired output. So for training, we need to know what we expect this model to produce. And then we learn all these matrices. So the final matrix looks funny because it produces only one number in the output. So we have to learn the correct weights of these matrices in order to create the correct map. And so we have a function which compares the output which is generated by the thing, which is completely random in the beginning, with a true value. And this function, actually, this is called the loss function. And this function, you can think about it that you have a landscape where at each point in this landscape is actually a set of weights. So this is extremely highly dimensional space, because if you have here hundreds of matrices of hundreds of dimensions, you have millions of dimensions here. And in this million dimensional space, you have a loss function, which will generate kind of valley, and it will generate height. So if the model is very bad, it has a high value. If the model produces exactly what you want, it has a low value. And so you start somewhere in the top, because in the beginning your model is really bad. And then you walk inside the space. What walking here means, you change the values of all the parameters here by walking along the gradient, by minimizing this function. You minimize the loss function, and to minimize it, you change the values of all the matrices inside. And by changing these matrices, you learn the function. So this is how machine learning and deep learning essentially works. You have a loss function, you have this kind of field here, you try to find the minimum, you walk in the space of these matrices until you reach local or global minimum, and then this is a trained model. And at this stage, you have fixed the weights in all of the matrices which are stuck on top of each other. Okay, another way of thinking about it is that actually what you do here is maybe similar to what I showed in the beginning with these patterns. You can think about it as transforming that each layer in the model, by going up, look at the layer below and tries to change the space, to somehow make some transformation on the space to get the relevant features. What does it make data special, which you would look at? So you feed the system with raw data, and you discover automatically by this training process the representations needed for detection or classification. So deep learning, which I presented, composed simple but nonlinear modules, and each transformation at one level transform it into representation at a higher, slightly more abstract level. And then you compose many transformations, and you can learn any function you want. And the idea here is following. Assume your basic raw data has this form. You have two sine curves. and you have to separate somehow let's say you have to separate here the green from the red spaces. And if you would do naive linear classification, you would always, you cannot have a straight line here which separates them perfectly. If you draw a straight line here, you would get a lot of the blue ones inside this field. So because clearly the best separation here is not a linear function. But if you combine this in this layer structure, what happens is that if you compute what happens in each layer is that the space is somehow deformed in this way. And now after the deformation, it's quite clear in the final step to find a linear function to draw a straight line here, which clearly separates green from red areas. So this is what also happens. So this is another way to think what happens in neural networks is that the neural networks find the correct transformations of your input space, of your data space, in such a way that if the final task is to classification, to separate the data in different regions, then they transform the whole space in a way that in the end you have just a linear function which is needed to separate it in two parts. And now we are entering the field which is important for us, because I'm interested in time series. So I need something which has idea that it's something evolving in time. So this is called recurrent neural networks. So here we have a clock, and I have this kind of architecture. I have an input at one time step 1. This is kind of neural network, one layer I showed you before, multi-layered neural network. But the idea here is I save the output of the previous step. This is my first time step, so I have no output before, so I have a 1 coming in, and I give y1 as an output. X comes in, I predict y1. Now the time goes on, so now I'm in the next time instant. Now I'm at time 2. I enter x2, but this loop gives me now the previous results. So y1 is coming back to x2, and now I predict y2. Again, now we are going further. This is the last step. x2 comes in. We had y1 going, y2, one step further in time. x3 comes in. I receive the output of the last step, y2 coming in here, and y3 is presented. So this is how we capture the time. So we have a recurrent loop. And then what you usually see if you read at the papers is a representation where unroll this recurrent neural networks in time. So you have again a time axis on the x, this is time, and you show it simultaneously. You have x1 coming, x2 coming and x3 coming. And you see that this one receives input from, so y1 is actually passed here to this one. And this is called hidden state then, and y2 is passed to y3 here, and actually here comes then 0 as an input, because this is essentially the same cell unrolled in time. And now you can train it simultaneously, and you see the output y1, y2, y3, which you see. Okay, now we will take this recurrent networks, and we will take quite a complex implementation of it called LSTM, long short-term memory, which, as the name says, has memory inside, but essentially it's the same idea as here, and we will apply it to our problem. And our problem is now directly in time domain, so we are not doing the transformation. An idea here is to train a model some way on nominal data, and then to quantify, because the nominal case, we know exactly what the true, we don't need the labels where what is anomalous or not. We just take nominal data, so it's a semi-supervised approach. We need a data set where we assume we know that the anomalies are very low there or not present at all. And then either we train a model which tries to predict the future from the past. So we ingest some past values, sorry for this, and we predict the future. Or we put in some data and I will go into more details here how it works, and regenerate it back. And we hope that following happens. Most of these models are only trained on nominal data. So if you train them on nominal data, they are perfectly fine to represent and predict the nominal evolution of the system. And now you use your data, you take the past value and predict the future, or you put in some time steps and reconstruct them back, and you get this red curve, which are the predictions. The predictions should be perfect for nominal data. But now you compare it with measured data in blue, and this measured data may contain anomalies. And you see it here, there are clearly deviations between prediction and the measured data. You quantify the error between them. So you compute the residuals, which is just the absolute error. And you say, well, if my model failed to predict this, if there is a big difference between predictions and measurement, this is an indication of anomaly. My model was trained on nominal data. Something is wrong with the data here. You define an error at which stage the error is big enough. So you need to define this maximal error value you want to tolerate. And in every time step which is above this error, you consider this field, this period of time, to be an anomaly. So let's look about how it works. Autoencoders. Autoencoders take, you can have here multiple time series. You put time series in and you get a time series out of it. And you put some like minute 1 to minute 2 of your time series and you get the same minute 1 to minute 2 back. Usually the layer in between is smaller than the input layer. And so what is happening here is when you train it only on nominal data. So in the training, the things tries to reconstruct exactly what was put inside. You put, I don't know, sine inside, you want to have a sine curve coming out of it, exactly the same, or nominal data. And usually what is happening, you can imagine that this internal space is some kind of weird, not a vector space, but some kind of a weird space. And in training, the model has learned that all your nominal states it want to recreate lie in this lower dimensional plane. So what the model is doing is if it receives this kind of normal state, in the middle of it, it just gets projected down in this lower dimensional space where all the normal states are there. And in these steps from here to there, it just projects it back and reconstructs it. If you provide now this trained model with anomalous data, a data pattern here which is crazy, two things can happen. By projecting inside here, it may land somewhere completely outside of normal states in training. So you can compute distance in this space, and you see that the distance between all your normal points and this reconstructed thing in this two-dimensional plane is completely large. And the second thing, what happens if you reconstruct it back, if you project it onto the top, you get something weird. Or this case happens, you project it down and it looks at like normal data, but if the model can only reconstruct nominal data, so it gives you the blue vector back. And so the input and output look completely different. You have a reconstruction error, which is quite high. It fails to reconstruct an anomalies. The other thing you can do is to use more advanced techniques sometimes, which is the generative adversarial networks. These are two neural networks playing a game. You have a generator and you have a discriminator. So the generator gets random inputs. It's a neural network which gets here a lower dimensional random vector, and it tries to create out of it a time series which looks exactly like normal data, but usually in the beginning it fails. And the discriminator gets a time series, either normal or from the generator, and it has to decide correctly which one is the right one, which one is normal data coming from normal data source. And so they play a game. The generator tries to fool the discriminator, and the discriminator tries to get better to understand when this thing is, when it's not getting a normal data, but the output of this thing. So you let them play a lot of time. You compute a special distance between the predictions. So here, and then you have a perfect generator. And you know now that after this training, if you provide here a random vector, the generator will generate normally looking time series, a time series which a discriminator cannot distinguish from a normal one. And now you can also take an encoder which is trained on generator output. So you take the output, you encode it, and you give it back to an autoencoder. So what it happens is that given any time series, it will always get these vectors which are very good for the generator to generate it back. And now you stack them together in first an encoder and then the generator. And you provide any time series. If the time series is normal, the encoder generates exactly this pattern. And the generator takes this pattern and generates the time series back. Very low error. And now an anomalous time series is provided, completely weird one. Encoder was trained on nominal data. It can only provide here the same distribution as before. It will always be some random distribution. And the generator is trained to take this random distribution and create exactly a nominal looking data. It can only generate nominally looking data. And so on non-nominal cases, the input and output will be completely different. And you have, again, a big error between them, which is an indication of anomaly. Okay, then you can look at something which is a predictor. You take your time series, you ingest past values, you train the model on nominal, again, on nominal data, you slice it up, and you provide it here history of past values and tell me, okay, I give you 20 past values, predict me the next one. What would happen in the future? And train it on nominal data. So it will be able to generate nominal predictions. But if the data is not nominal, the prediction here will be completely different from the actually measured data. And in any of these cases, you will get the result in the beginning. You will have a discrepancy between the generated predicted output and the actual one. And of course, here are a lot of choices. How many do you put here? Multivariate time series? Do you predict the next step? Do you leave a gap? So here you can have a multiple various of parameters. So you can leave a gap. You can predict the 10th time step. So I give you last 5 seconds and ask you to predict me what will happen in 20 seconds. And I can predict 1 point in time, or I can predict even 10 next time steps, or 10 time steps in the future after a 5 seconds break or something like this. This is another architecture which actually we are using. This is very similar to autoencoder, but this is a layer, as you see, we provide here time series. We take the final encoding of our STM and we put it into another one as input. That is the same input here, which is an encoding of the whole time series. And then we provide this thing as a decoder, and it tries to reconstruct the same time series back. Kind of encoder-decoder, a little bit different architecture. I think to these details, we have to go more into with the questions, what you're interested in. Okay, now we have a difference between what we predict and what we measure. And now we have to put somewhere a cutoff. We have to say, okay, now the difference is big enough. Now it's an anomaly. And there are various ideas to do it. The simplest one, if you have a sample of data which you know contains very little anomalies, so you just create a lot of these plots, or you create a lot of these differences, and then you compute the statistics about the high, so how big the difference actually is. You compute a whole statistics of it, and then you can select the 99th percentile and say, okay, I will consider everything to be an anomaly if this error value is higher than the 99th percentile of my data, which is considered to be normal. This is kind of works well if training contains known proportion of anomalies. Assume you know to 100% that the data you train on contains no anomalies whatsoever. Then, of course, if you select something like this, you will generate false positive results, because by definition, 1% of your data, even if it's nominal, will be considered to be above the threshold. The error will be high enough there. So you have to go beyond the data you had. And there you can use extreme value theory to create a theoretical distribution of the errors and go beyond what is measured. So also very technical detail. If you're working in this field, if you're interested about it, we can talk about it later. Okay, here, advertisement, we have created a library which covers a lot of the topics I presented so far. Currently, it's internal library. We are thinking about open sourcing it in the future. This is work to do for me in next year, so be aware that it might come out. Some results. So we had a validation sample with known anomalies. So in total, we had 82 sensors. We have 200 sample flights for training, assumed to be normal. We had 100 flights containing 5% labeled anomalies. And this is, again, the picture. So in red is what we predict for one sample. In blue is the actual measured flight. In green here are the differences, the error between prediction and measurement. And the values here in this red regions are above the cutoff and considered to be anomalies in time. And one of our best models, so we have actually now a better model, but here what these numbers tell you are, we find 76% of all anomalies present in this data set. It's quite good. We are actually quite better right now. We are above 80. And we not only find all of 76% of them, if we present these anomalies to engineers in the end, we will definitely find false results also. But in the end, out of 100 anomaly candidates presented to engineers, 67 will be true. So this is the precision, and which we also now are able to put above 70%. So this is very important, because if you create a model like this and you work with real engineers on the other end, and your model is great, it finds all anomalies, but it also finds hundreds of other hits, and all of them are wrong, nobody will use your model. So you really need a model which provides high accuracy, high precision, in order for engineering world or for any other world to take it seriously. Okay, and this is what we are deploying. So if you are interested in the technical background, we have on-premise data lakes containing all the data, the events, and the flights. We use AWS, so Amazon Web Services architecture. We retrieve automatically new data, which is ingested after flights. We get the sensor data. We run the anomaly detection module on AWS SageMaker, which is pre-trained model by us. If something is found, we notify the users. They are able to open a web application, completely secured, which allows to see anomaly as a see time series, display the flight data, and edit the anomalies and provide the feedback back to us. And so we enrich our data sets and create better and better understanding. These are some references. So thank you very much. And I'm very much welcome to receive your questions.
Thank you. We have some questions and comments. And I remind you that you can ask your questions in comments in English or in Russian or in Ukrainian. So first question is, when you talk about flight data, what do you consider as anomaly?
Okay, so there are different kinds of anomalies, of course. So usually airplanes are extremely safe. So I am talking about very small deviations from behavior which is expected. So for example, you know that you have a system which should evolve in time, and it's, I don't know, for example, a valve. It should open when the pilot says open, it opens. When the pilot says close it, it closes, and then it just stays closed. If this valve starts to operate by itself, starts to open and close, even without endangering anybody, but it still is operating somehow, this is an anomaly. Or you expect that there is a command, something happens, and you expect that it's an oscillation. So some signal starts to oscillate, it's transitory electrical behavior, and it dies out. Okay, but if nothing changes and oscillation starts to evolve and then it dampened out by the controllers, it's still an anomaly. Or if temperature reaches a value which is okay, but it's maybe too low as expected, because there are requirements on every part of the plane. We know how the system should evolve, and even if it's not dangerous in any way, but still unexpected, this is an anomaly.
Okay, thank you. Another question is, do you know something about searching hidden anomaly algorithm based on hidden Markov models? It's interesting to hear about testing stage given a known time series.
Yes, so there are some models like this. There are some teams working on it. So we were, since I came from the AI department or AI directions, so we implemented these AI models, deep learning models, and haven't looked into hidden Markov models. But there are some works in this direction. So far we are quite excited and happy about this result. So we are going forward in this way.
And one more question: for what purposes is machine learning still used in the aviation industry, except that you talk?
In any direction. So starting, I mean, aviation industry is an industry as any other. So we can use machine learning in finance, HR, optimization, procurement, logistics, production. We have, of course, very advanced projects with computer vision, where there is a demonstrator called Atoll, which is a project with a Silicon Valley spin-off of Airbus, which demonstrated autonomous landing by vision. So yeah, there are like plethora of dimensions to work with. We are focusing in my team on projects which deliver actual business value in foreseeable time. So a lot of optimization projects, a lot of using NLP. We have a lot of documents on files. We have to scan and understand the knowledge, extract the knowledge and combine it. Something like this, yeah.
Okay, can we switch to Russian now?
Yeah, да.
Большинство наших слушателей студенты Харьковского авиационного института, поэтому я хотел бы, чтобы вы еще рассказали, можно ли попасть на стажировку в компанию Airbus, в ваш офис, или что нужно для того, чтобы попасть на работу выпускнику?
Очень хороший вопрос. Это зависит, мне кажется, от того, где находятся офисы Airbus в стране. Что я знаю, что есть какие-то офисы в России, на территории России, где-то рядом с Москвой. Я не знаю, как это на территории Украины, к сожалению. Я знаю, должны быть какие-то... Явно есть программы по проходу стажировки, но я знаю больше о них на территории Европейского Союза. Я бы посоветовал просто написать на все номера, которые можно найти в интернете, и спросить об этом. В основном мы об этом довольно открытая организация. К нам в наши команды в основном попадают люди, которые уже работают в Airbus и проходят внутреннюю стажировку. У нас большая программа стажировки по искусственному интеллекту и аналитике. Я знаю, что есть программы по стажировке, допустим, в Англии есть государственные программы, где многие, кто начинает работать в компаниях, проходят стажировки в разных отделениях. Я не видел у нас напрямую студентов, даже в Германии у нас пока еще студенты есть, в любом случае есть студенческие работы. То есть мне кажется, что есть для студента возможности попасть, но я бы написал в офисе Airbus. Да.
Какая роль вашего департамента? Сказали, что вы работаете в департаменте искусственного интеллекта.
Да.
Сколько человек, у вас какая-то часть компании?
Я работаю напрямую в Airbus Commercial, то есть коммерческие, производящие самолеты в основном, да. Есть, так как Airbus делится в некоторые отделения, это Airbus коммерческие, то есть самолеты, потом Defense and Space, это космос и защита, и вертолеты. Каждое из этих отделений имеет свои, отделы информационных технологий и искусственного интеллекта. У нас мы были частью организации так называемого офиса трансформации, цифровой трансформации, DTO, Digital Transformation Office. И сейчас мы, так как мы проводим все больше и больше проектов, мы часть организации департамента IT. Наша цель не делать все проекты для всего Airbus. Например, одна из больших целей нашей организации – это взять, как это сказать на русском языке, знания об этих темах и дать эти знания инженерам во всех департаментах. То есть во многих департаментах, в инженерных отделах, в финансовых, в персональных отделах сидят люди, которые прошли внутренние стажировки, которые занимаются этими темами. Но если проекты становятся больше и больше, они могут прийти к нам и получат помощь. Кроме этого, мы пытаемся создать большие платформы вокруг центральных тем, важных для Airbus, допустим, computer vision, anomaly detection, knowledge extraction, NLP, natural language processing, и дать всем работникам или какие-то tools, программы, платформы, чтобы они могли сделать эти продукты. То есть мы, как бы центральная команда, но наша цель не взять всю работу на себя, а принести ее к людям в бизнесе, которые производят прибыль для нашей фирмы, конечно. Да, такая роль.
Среди задач, которые вы упоминали, была обработка естественных языков, компьютерное зрение. Как это применяется в авиационной отрасли с точки зрения прикладной? То есть где, например, применяется компьютерное зрение или обработка языков или другие задачи?
Это зависит, конечно, от того, ну, допустим, если смотреть в сторону будущего, то, конечно, компьютерное зрение, как я уже сказал, применяется даже в самих самолетах для некоторых целей. То есть в будущем, очевидно, будут системы, которые будут позволять, может быть, пилотам садиться автоматически на аэродромы, без которых нет системы автоматической посадки, которые существуют сейчас. Но, допустим, компьютерное зрение очень важно даже для производственных процессов, когда она смотрит на само производство и понять, что происходит там. Также осмотр самого состояния самолетов перед проверкой того, находятся ли все компоненты на нужном месте. Я бы сказал, это, с другой стороны, тонкий вопрос, потому что это еще связано с правами работников. И в Европе мы занимаемся также защитой данных, то есть GDPR, General Data Protections. Поэтому мы стараемся взять это все в условия и, допустим, в некоторых даже производим это все так, что это действительно приносит value для всех, но мы не снимаем, допустим, людей, мы снимаем именно производственные процессы. С языком это очень важно. Natural language processing очень важная тема, потому что много знаний находится в текстовых документах. Если мы хотим экстрахировать всю эту информацию, понять ее, то надо понять, как что там написано. Причем мы находимся в разных странах, поэтому эта система должна читать текст, который написан инженером во Франции на английском, но может быть также написано французским техником на французском или немецком на немецком. То есть у нас смесь, в некоторых документах даже смесь языков.
Супер. И последний вопрос. Что бы вы посоветовали молодому специалисту или студенту, который хочет развиваться в области искусственного интеллекта? С чего начать, как идти дальше, каков путь?
Ну, это зависит, конечно, от собственного интереса. Я думаю, что сейчас самое лучшее время этим заниматься в интернете очень много разных программ обучения на разных уровнях. Я сам, у меня мой, как бы сказать, мой background, я начинал учиться физикам, то есть я теоретический физик по обучению, поэтому я привык учиться еще из книг, то есть я начал читать книги. Потом я делал тоже те же самые известные курсы, Coursera, ettern. Потом я, конечно, стал программировать. Но я много об этом уже знал, программирование, конечно, знал с моих предыдущих работ. Мне кажется, если нужно иметь действительно интерес к этой теме, это не просто тема хайпа, которой сейчас все хотят этим заниматься. Конечно, это тоже так, но с другой стороны, она может принести много больших шагов вперед для всей индустрии, для всей аэронавтической индустрии. Она может помочь к следующим большим, как бы сказать, через следующие течение 10, 20, 30 лет вся авиационная индустрия должна понять, как уменьшить выброс CO2, CO2, углекислорода, углерода, да. И поэтому это интересная тема, ей нужно увлекаться, и я бы посоветовал начать с интернета, посмотреть в интернете, и там есть куча разных курсов, Coursera, допустим, известная, довольно хороших, есть пару курсов даже свободных на YouTube от Caltech, они, может быть, даже немножко старше 2012 года, но они хорошо показывают математику, которая находится за всем этим. И я бы мой совет от меня не просто учиться по интернету и делать только программы, но попытаться понять всю математику, и статистику, которая основа этого. Потому что даже если в продакции, очень часто, если люди создают великолепную модель и говорят, что она великолепна, 80% аккуратности, но когда ты применяешь ее в продукт, когда ты ее даешь людям, они начинают с ней работать, вся система рухнет, и просто вся качество ухудшается. И это от того, что люди не понимают, какие статистические проблемы могут возникнуть в связи с данными, если ты тренировал на одних, а использовал на других, то я бы советовал заняться статистикой тоже. Да.
Спасибо большое. Спасибо за ваше время. Уверен, что это было полезно нашим слушателям. Небольшой анонс еще хотел бы сделать. Завтра поговорим, собственно, про космос с экс-главой Украинского космического агентства Владимиром Усовым. Во вторник поговорим про искусственный интеллект с Head of Machine Learning одного из самых горячих стартапов этого года, компании Aerospace. Спасибо еще раз, Сергей, за ваше время.
Пожалуйста, всего хорошего всем, хороших праздников.
Всего хорошего.
Всего хорошего. До свидания.
До свидания.